Okay, so this one is going to be a little bit more difficult than the two we just completed because we have a tension cable, and so we're going to have to be able to write a Cartesian vector that represents where it is in space. And we have a force that's acting in this direction, so we'll also need to be able to write a Cartesian vector so that we can get the x, y, and z components. Okay, so we want to determine the x, y, z components of the pin at A and the tension cable, tension BC, necessary for equilibrium. So this is like a door hinge. Okay, it's just like a door hinge. If I take it and try to pull it left or right, it is not going anywhere. If I try to pull it towards me, not going anywhere. If I try to pull this thing up, it's not going anywhere. The only thing that would happen is if I'm looking at the x-axis, here's my x-axis, and I pushed up here at B, it's going to rotate. So it's much like the pin if you have a pair of glasses, okay? It's much like this pin. It is not going anywhere. X, Y, Z, I can't pull the earpiece off. I can't rotate it around the Z. I can't twist it, torsion around the Y, but if I push up, I have nice rotation around that x-axis. So I develop every force except rotation about the x-axis. And this is the best way for me to be able to see what is happening with a, especially a 3D reaction. Okay, so now that I know everything develops here and then I have tension, I need to get this drawn. Free body diagram is key. And use a straight edge. Okay, we don't expect total perfection, but it needs to be neat. Okay, it makes life easier. You can see what you're doing. It's easier for us to help you. And don't be afraid to use all of your paper. Okay, so here is my X, Y, and Z system. And when I look at it, I've got this little piece that comes out following the y-axis, and I'm going to make that a little bit thicker just so I can see where it is. Okay, and then it looks like B comes out and follows parallel to the x-axis. We have a 90-degree hook right here. And there we go. Okay, so there's my frame, if you want to call it that. And I develop resistance, everything except for a moment about the x. So I have a force in the x direction. I have an unknown force in the y direction. I have an unknown force in the z direction. I have an unknown right-hand rule positive moment about the y. I have an unknown right-hand rule positive moment about the z. But again, I can actually rotate right there around the x-axis. Okay. Now, if I look at this cable, it is pulling back towards the wall, and I can see, okay, it's kind of going in this direction. And I'm just going to put a dotted line in there right now because I'm going to end up finding the components, and it's easier for me to see instead of a vector in 3D pulling this way if I can actually see the X, Y, and Z components. I also seem to have this little nub coming out, and it needs to be parallel. It is parallel to the x-axis, and it has a force that's pulling down to this spot, something like that. So again, I know it's going to be going in this direction in 3D, but I'm going to have an X, a Y, and a Z component. And it's just easier for me to see once I calculate those, what they actually look like. So I have B, I have C, I have this little force here, and I have A. So now I need to kind of dimension. If I'm looking at C, we can see that coming down and coming over, we are 4 feet over and 5 feet down. So that's going to give us, I am at -4, 0, 5 feet. If I come over here to B, I can see I am 12 feet down this length. I go 4 feet in the negative x direction, so I have -4, 12, and 0. Okay? If I look at this part right here that's coming out, I need to have its components, and I can see that we come 2 feet down the x-axis, 4 feet down the y, and it is at 0. And down here at this point down here, okay, we come 10 feet along the x-axis, okay, 12 feet along the y-axis, and -4 along the z. And all of these are in feet. So I have -405, -412, 0, 10, 12, -4, 0, 0, 0, and 240. Okay? So with all of these unknowns, I'm going to need to sum all of my forces. And I'm going to need to sum all of my moments. Which means I need to find the x, y, z components of both of these, the tension cable and the applied force. So let's start with our force vector. So this is kind of a good review of Cartesian vectors. And I know that a force vector is F times the unit vector. And we're going to call that of F, which means we have position vector of F divided by magnitude of F. So, position vector of force F equals tip minus tail. Pulling in this direction, tip minus tail. 10 minus 2i plus 12 minus 4j plus -4 minus 0k feet. And when we simplify, we get 8i plus 8j minus 4k feet. Now, I need to find the magnitude. That is just using Pythagorean theorem. We have 8 squared plus 8 squared plus -4 squared. And when we work this out, we get 12 feet. It's beautiful when things work out to whole numbers. Okay, so our unit vector, so we got this. Now we need to make it the unit, is position divided by magnitude. So I'm going to have 8 divided by 12, 8 divided by 12, -4 divided by 12. 8 divided by 12i plus 8 divided by 12j minus 4 divided by 12k. Feet over feet goes away, so it is indeed unitless, and I can simplify. If I want to, I could call this 2/3 I plus 2/3 j minus 1/3 k. Okay, check. Now I need to multiply by the force. So force of 350 pounds times 2/3 I plus 2/3 j minus 1/3 k. Okay, and I'm going to get 233.33 I plus 233.33 j minus 233.33 k. And I have units of pounds. Okay, units of pounds, which is perfect because it is an applied force. How can I check to make sure this is a unit vector? 2/3 squared plus 2/3 squared plus -1/3 squared should equal 1. How can I make sure this is indeed my force vector? 233.33 squared plus 233.33 squared plus negative, that is not even the right numbers, it should be half of that. This is where I have my friends in class that can say, hey, wait a minute, Professor Emerson, you did your math wrong again. Okay, so if I take these, see, and that's where I could have easily found I made a mistake, because 233 squared and 116.67 squared, add square root, and I get 350. If I had made a math error, this is really awful today, I'm so sorry. I don't know why it's continuing to come out of focus. If I had actually used the 233 here, I would have gotten 404, which is not the force I started with, and that would have been a clue. I need to go back and figure out what I did wrong. Okay, so we have our force vector. This means x, y, and z. If I go back up here, now, I know that the x component, I'm going to erase this, it's in my way. The x component is pulling positively at 233.33. The y component is acting parallel positively at 233.33. And the z component is acting in the z direction, negative, down, 116.67 pounds. Okay, I can also see that we are 2 feet out and 4 feet back, so that'll help. So to me, this is just much easier to see than a force vector that's just kind of going to nowhere. Okay, now we need to do the same thing for our tension cable. Find a piece of scratch paper. So we have the tension cable. It is tension from A to B. Okay, it's going to be the tension in that cable times the position from A to B divided by the magnitude from A to B, which is the same thing as the unit vector from A to B. Okay, we don't know this tension, so we'll be using TAB as our variable. So let's start with position. Position from A to B equals tip minus tail. It is pulling this way. Tip is at C minus tail at B. C minus B. -4 minus -4. -4 minus -4. Make sure you keep up with correct algebra and you don't call this -8. Okay? Let's look at B. Tip minus tail plus 0 minus 12J plus 5 minus 0K feet. When I simplify, I'm going to have 0I minus 12J plus 5K feet. And I mean, that makes sense. They both are set over by the amount of 4. Okay, so their x component, this arrow is in the YZ plane. It shouldn't have an x component. Now I need to find the magnitude. So we use our good friend Pythagorean theorem. And we should know this one by heart because we use a lot of 5, 12, 13 triangles. Okay, so if I said to you, how much cable do I need to put this tension cable in place? What's the length of cable I need? 13 feet's the minimum. I would need more to tie in, but it's 13 feet from B to C. Okay, so our unit vector, from A to B, well, it is from B to C. Why am I calling this? It's late and I'm tired. I apologize. And I don't want to start over. I don't know where that came from, because clearly it's going from B to C. B to C. Okay, sorry for that confusion. B to C, B to C. Okay, anyways, you understand what I'm talking about. So we're going to be dividing. So I have 0 over 13I minus 12 over 13J plus 5 over 13K. And it's a feet over feet. Unitless vectors should be unitless. And how can I check to make sure this is a unit vector? This squared plus this squared plus this squared, square rooted, should equal 1. Why do I have this here if it's 0? So that when I go back to draw my forces at B, I remember that I don't have a force in the x direction, and that works out fine. Okay, it's a placeholder in my brain. So the tension from B to C as a vector is tension BC times this unit vector. And when I multiply this through, I'm going to have 0I minus 12/13 TBC J plus 5/13 TBC K. And so these are my components that I'm going to go back and put onto my little diagram. I have nothing in the x. My y is negative, which makes sense, is following the direction of my cable. My z was positive, which makes sense. It's following the direction up. And I have 5/13 TBC, and I have 12 5/13 TBC in the y direction. So I now have this nice little free body diagram with my unknowns. I have my force vector and my tension cable broke into XYZ components, and I drew them on here in components so that I can just see the moments and forces that are being created. So now we get to do the fun part. Well, I guess that was the fun part, but we're going to start with summing forces in the x direction, positive coming out towards me, f of x equals 0. And I'm going to start here at my unknowns. F of x does indeed develop a force, positive Fx. We're going to come around here. My force vector has a positive 233.33 pounds. My tension cable does not have an x component. That's kind of lucky for us. So this all equals 0. So F of x equals negative 233.33 pounds. Again, if we were in 2D, I would tell you take the negative away and show me that it's going in the negative direction. But with 3D, you need to start with everything positive. Okay? So now we're going to sum forces in the y direction. We do develop a force in the y direction, positive. We're going to come around here. We do have an applied force, 233.33 pounds. We're going to come around here. We do develop a resisting force, minus 12/13 FBC equals 0. So this one's not as helpful. I still have two unknowns. Let's sum forces in the z direction. Up is positive. We develop a force in the z direction. We're going to come around here. We have a negative 116.67 pounds applied. And we have a positive 5/13 tension BC. I keep calling it tension or force, and I'm kind of confusing those two, but tension BC equals 0. So we have 1, 2, 3 unknowns. We only have 2 equations. We're going to have to keep writing equations. So let's sum moments about the x-axis. Coming out positive right-hand rule, wrapping around to the left is 0. We do not develop a moment about the x-axis because it's like my hinge on my glasses. I can actually go choink it, choink it, choink it, and rotate. So that'll be nice because we'll be able to solve for something now. So let's go to the applied force. It has an x component. The x component cannot create a moment about the x-axis. The y component, because it's in the same plane down here, will not cause a moment, but the z component, okay, the z component could cause this to rotate about the x-axis. So the z component would be like pulling down, and I can have rotation, and it looks like positive, it's going to be a negative rotation. So I have negative 116.67 pounds, okay. Its perpendicular distance back to the x-axis is 4 feet. Okay, so we're done here. Let's go here. If I look at the y component, it's in the xy plane, so it would just cause pushing. But the z component here, again, here's my x-axis on the x, sorry, my fingers are in the way. Here's my x-axis, and I can indeed, if I push up, I'm going to rotate. And that is positive, so I have positive 5/13 TBC equals 0. So we can use our algebra to rewrite this. And I can get that my tension in BC is 101.1 pounds. And it thankfully came out positive because it is indeed in tension. So now I can go back here and I could actually substitute that in, bring both of these over, and I'm going to find that FZ equals 77.78 pounds. And I can plug my tension here, bring these over, and I can find that FY is 140 pounds. So I have 1, 2, 3, 4 things solved for. I still need to find this resisting moment around the y-axis and the resisting moment about the z-axis. So let's sum moments about y. Coming out of the page, right-hand rule positive. We don't know what that value is. So that starts our equation. And now we have to come back and do the same process. If I'm going about the y-axis, that's this axis right here, the x-axis translation, it's in the same plane, no rotation. Y-force, parallel, no rotation. But this z, if I'm looking at rotation, the z-axis could wrap around, and it's wrapping around positively. So we have plus 116.67, and it has a perpendicular distance of 2 feet back. Okay. The y component here, parallel, not going to cause rotation, but we do have this z component coming up and around. So plus 5/13 TBC, and it is set back 4 feet equals 0. Well, we actually have a value there. Both of these are positive, but when I take them over using algebra, they become negative. So my equals negative 388.89 pound-feet. Remember, moments have units of pound-feet. Okay. Summing moments about the z-axis. Up, right-hand rule positive, wrap. I have a moment around my z-axis that develops, and I have to do the same thing. The x component, could I cause rotation about the z-axis? If this were a clock handle and I pushed on it, would it rotate? Yes, it would. Would it rotate positive or negative? Thumb down, so we have negative rotation. So I have mz minus 233.33. Its perpendicular distance is 4 feet back. Okay. Y component, would it cause rotation? Well, it's offset. So if I pulled a clock handle that came in this direction, it would indeed rotate, and it's rotating positively. So I have positive 233.33 times 2 feet. The z component, parallel, nothing going to happen. If I look over here, the z component, parallel, nothing happens, but I do have this y component that is causing, okay, positive rotation, so plus 12/13 times TAB, and it has a perpendicular distance back of 4 feet equals 0. I do have a value of TAB, so I can plug that in. When I solve all of these things, rotate them over here to my 0 side, I get that mz equals negative 93.74 pound-feet. And there you have it.